Okay, so let me introduce rainfall modeling, which I already anticipated to you briefly during the past couple of hours. This is the slide that I will use, and I will also use the blackboard, and maybe that when I use the blackboard, maybe that I need to turn the light on. And the slides are already available on my website. And be careful that I put on the website some new material yesterday and not today. So, as I anticipated, rainfall runoff modeling aims to reproduce river flows starting from rainfall. And also you need much more information. You need information on the watershed or catchment. I will use the terms watershed, basin, and catchment as synonyms. Basically, there are differences in American English and British English. Let's treat them as synonyms. And my preferred term is catchment, but in any case, we can use the terms as synonyms. And we need information on the catchment. We need information on the soil properties, the vegetation cover, and also we need information on human impact, anthropization, urbanization. Because as I said, in this rainfall runoff transformation, humans are playing a very important role. The purpose for us is to be able to get information for water resources management. Rainfall runoff models are used also for other purposes like big flow estimation, like design of bridges or other river engineering works. For us, the purpose is water resources management, which means that we are interested also in low flows, not just peak flows. And this is a more challenging problem because low flows are more difficult to reproduce than peak flows. Basically because low flows are governed by storage, water storage, and not just water transfer. And water storage is a bit difficult to reproduce because it takes place mainly underground. Among the uses that can be done of rainfall runoff models, there is also forecasting. Forecasting means real-time prediction of future river flows. This is much different with respect to simulation of past river flows. For instance, you have seen that for the water plan of the Emilia-Romagna region, we tried to reproduce the river flows in the time span 1991-2000. This is a reproduction simulation of past river flows. It's a different story than prediction of future river flows. For instance, prediction is needed when you see that a flood is coming, and you want to decide if we need to evacuate a region, some houses or not. This is a typical application of real-time flood forecasting, which we will not consider in this course. We will consider here just simulation of past or hypothetical river flows. Hypothetical means river flows that never occurred, but we are interested in generating because we want more data. So let me be more clear. So we can divide the application in two main groups: simulation on one hand and forecasting on the other hand. This is, for instance, flood prediction. Simulation can be divided into subcategories. Simulation of past river flows, and simulation of synthetic data or hypothetical data, as I called them before. So I think I already clarified the difference, the meaning of flood prediction, forecasting. It's clear. I think it's also quite clear what is a simulation of past river flows. It means that you take past rainfall, you feed with past rainfall and other data, required data, the rainfall model, and you get a simulation of past river flows to be eventually compared with what you observed if available, or if they are not available, the observed data. In any case, you get an estimate of what happened in the past. Finally, you might be interested in what is called simulation of synthetic data, which means flows that will not occur in the future and never occurred in the past. They are hypothetical data. And so your question could be, why I'm interested in simulating hypothetical data? The interest is because if you want to test a water resources management policy with respect to an extended data set, and you have only like 2 years of observation, you may want to extend the data set by simulating with synthetic data. They are data which never occurred, but which could occur in the future or could have occurred in the past. They are equally likely as observed true data. And your question could be, why do I need to simulate synthetic data? Why shouldn't I stick on the simulation of past river flows? And the reply is very simple. If you have observed rainfall data, then of course you prefer to use the observed rainfall data and simulate the past river flows. But if you don't have the rainfall data, you need to generate the rainfall data first, hypothetical, and then as a response to hypothetical rainfall data, you generate the hypothetical synthetic river flow data. So if you have observed information, input information, you can use simulation of the past. If you don't have neither observed river flows and observed input data, you need to refer to a hypothetical situation. And this is the simulation of synthetic data. What the Emilia-Romagna region did for the period 1991-2000 was a simulation of past river flows. They had rainfall, temperature, because sometimes you also need temperature. You will see when, we will see when. And therefore they simulated a past situation. But if they did not have this input information, they could generate it by referring to a hypothetical situation. One distinguishing feature of flood prediction, of forecasting, is that you can check after applying the model if the model was correct. Of course, you make a prediction of a big flow, you decide to evacuate like some houses because the model tells you that a flood is coming, and you will see after a few hours if the flood comes or not. So you have a verification of the model as soon as you have applied it. This is a distinguishing feature. In the case of simulation of past river flows, you may have some observed values. And if you have them, then you can check the validity of the model. But you may have not. You could be in a situation where you don't have any past river flow available. So in this case, you couldn't check the model. And in the simulation of hypothetical data, synthetic data, you don't have the observed data because they never occur and they will never occur. So you can't check the model. You have to find, if you want to check the model, you have to find alternative ways. So these are the basic applications. We are interested in these simulations, even if in water resources management, sometimes you are still interested in prediction. For instance, if you predict the droughts, how much the drought will last, the drought is mild, right? Then forecasting may be useful. But the great majority of application of rainfall runoff models in water resources management is simulation of past or synthetic data. As I said, rainfall runoff modeling is a well-established branch of hydrology. There are a lot of contribution. There is also there are some textbooks. Even if I had to recommend a good book on rainfall runoff modeling, even in English, I wouldn't have a clear idea because you know, it's still an evolving subject. It's already used in practice, but I would say that the practical application of rainfall runoff modeling started just, let's say, a couple of decades ago. It's a field that is underdeveloped. These are some slides that I think I can skip because I already explained to you what is our aim, is to estimate water resources availability, and therefore I think I can skip this. And also I can skip this because we already discussed the hydrological cycle, and also I can skip this slide because it is just a way to show to you, but we will have the opportunity to discuss later on these issues, that the rainfall runoff transformation is very much complicated. I already mentioned to you when we spoke of the hydrological cycle that there are a lot of phenomena that are interacting in the hydrological cycle. And here you can see a different sketch where you have to account for not just for what happens in the surface, but also for groundwater infiltration. For overland flow is what happens on the surface, but then you have infiltration, groundwater recharge, groundwater flow. And these phenomena, in general, are to be simulated by the mathematical model. In some cases, you can neglect them. We will see that we will try to simplify the mathematical model. But in principle, the phenomena is very much complicated, including evaporation, transpiration from the vegetation, etc., runoff to streams and the ocean, etc. A lot of things. So, in principle, it is a very complicated process, physical process that takes place. In some cases also including chemical processes, which is difficult to reproduce. Okay, let me introduce the basic of rainfall runoff models. And let me make clear that sometimes these models are called hydrological models. Hydrological models is a broader category. Hydrological models means mathematical models of the hydrological cycle, which of course includes rainfall runoff models. Rainfall runoff models can be considered a subset of hydrological models. For instance, other examples of hydrological models could be the models of the aquifers, groundwater models. They are hydrological models. But in some cases, the literature uses rainfall runoff model and hydrological models as synonyms. Let's keep in mind that in principle, it's a more extended set of models, what is included in the set of hydrological models. So the question is, how can we build these models? How can we build a rainfall runoff model? This is the basic question. It's a mathematical model because, of course, we need a relationship, which is a mathematical relationship that gives us the river discharge, let's call it Q, which is a time-varying variable, and the river discharge must be estimated through a mathematical function, f, which depends on a series of input. Let's say that I call the input with the letter capital I, where I is a vector. Sorry, ID is a vector, including rainfall, temperature, watershed behaviors, I mean, etc. So this is a mathematical relationship. So the natural question is, how can we build this mathematical relationship? And I'm talking in the singular, but this mathematical relationship may be a system of equations. It depends on the number of unknowns. In this case, I just wrote one mathematical relationship by indicating just one unknown. So it's a very simple representation. An output which is depending on an input. But keep in mind that in the system, in the hydrological system, there could be other variables which need to be described. If I want to relate the river discharge to rainfall input in general, I may need to introduce other variables. State variables. Let's consider very simply the water storage. The catchment is a system that receives water from rainfall, can store the water, and then delivers the water in the form of river discharge. So the storage is very much important, because if the catchment cannot store water, then it tends to deliver an immediate reply to rainfall. But there are catchments that can store water, and if they can store water, the reply to rainfall is different. And therefore, this storage, which we often indicate with the letter W, it's a variable that is not a variable of direct interest. If we are interested in just the river flow, storage can be for us not significant. But still, it's a variable that we need to describe if we want to relate the river discharge to the rainfall. And therefore, it's a state variable because it quantifies the state of the system. If it rains over a basin that is dry, the response, the hydrological response, is different with respect to the situation in which it rains on the basin that is wet. The difference is storage. In one case, it rains over a basin that is empty of water, and in the other case, it rains over a basin that is full of water. So this is a variable that quantifies the state of the system. It's a state variable. So when we talk about an hydrological system, we have, of course, an output variable, which is at least one. We may have more than one, because I may need, besides the river discharge, I may need the water level, the water height in the river, because if I'm interested in flooding, the river discharge is, I forgot, sorry. It's not really what is significant. What is significant is the water level. So, and also I have to identify any state variable that I need, and therefore I have to identify the unknowns. So if I have just one unknown, I may have only one equation. If I have 10 unknowns, I need 10 equations. So again, what is the question? How can we build this? Before trying to reply to this question, let me show you a figure which quantifies, which gives to me the opportunity to speak about catchment, state variable, hydrological system. Let me see if I can, yes. No, just one second. Let me increase the size. I think it is on the screen, yes. And let me just for 1 second darken the room. Now, these are 2 catchments located in Austria. They are very different, and you see here typical hydrographs, which means the hydrograph is the plot of the river discharge against time. Hydrograph is defined. If we draw a plot of the river discharge against time, it's an hydrograph. While the hydrograph is the plot of rainfall against time. Now, if you see, these are hydrographs drawn in different seasons. You see the seasons here. And have a look not only at the river flow, but also the river flow, but also the shape of the hydrograph. And let's note that on the left we have a basin, a watershed that is extended for 432 square kilometers. On the right we have a basin that is less extended, is about half extension, less than half extension. But you see that the magnitude of the river flow is much higher in the second catchment. In the catchment on the left, what you see is that the peak flow is about 1/4, but if you look at the volume of water delivered by the hydrograph, what is the volume of water? Is the area below the hydrograph. Because, you know, if you have an hydrograph Q, depending on P, and it is this one, the area that is under the hydrograph is the integral of the hydrograph. And what is the integral of the hydrograph? If you make an integral between 0 and t of qt and the t, this is the integral of the hydrograph. And what is this integral? It is the water storage. Is not the water storage, sorry, is the volume of water delivered by the hydrograph. Because if the discharge is defined as the volume of water passing through the river for unit time, if you take the integral along time, you get the volume of water. So the area below the hydrograph is the volume of water delivered by the hydrograph. And you see that on the left graph, the volume is much higher. And this is what you would expect from a basin that is twice extended. You would expect, if the rainfall is comparable, and this is in Austria, so in Austria is small, rainfall is comparable, you would expect to get more water from a more extended catchment. And this is what happens. But by contrast, the peak flow is 4 times higher in the smaller catchment. What is the difference? The difference is that this catchment stored water. This catchment not. You see, in this catchment the hydrograph lasts for a longer time, much longer. In this catchment the hydrograph finishes soon. Why? Because this catchment stored the water. So if the catchment keeps the water, then of course the hydrograph continues for a longer time. Because it takes a longer time for the catchment to release the water. Instead, when you have an immediate response, you don't have storage and the peak flow is increased. Fast response, peak flow increased, less storage. Slower response, you see it takes more time to get to the peak water storage and lower peak flow. And look at the shapes. You see they are very different. In this case, we have mild slopes, reduced slopes, and you have cultivated fields which favor infiltration. And when you have a reduced slope, infiltration is favored. In this case, you have steep slopes, which means higher velocity of water on the slopes means less infiltration. So it's much important to look at catchments. We are talking here not about mathematical model. This is important that you really get this concept. This is not a mathematical model. This is a physical system. We are talking about a physical system, so look at the physical system first. When you talk about hydrology, when you talk about catchments, you are talking about things that we are used to know, because it's our surrounding, it's our environment. Look at the catchment first. And then, of course, you need to write a mathematical model, but you are still dealing with a catchment, with a real system. So the first thing to do in hydrology, and especially in rainfall modeling, is go there, look at the catchment, try to elaborate an idea of how the catchment works. So you see a picture like this, and you're able to say, this is very steep. So I expect a peak flow that is higher, and I expect a recession curve. A recession curve is the descending limb of the hydrograph, is this part of the hydrograph. I expect a recession curve which is less lasting, which means also from the point of view of water availability, means that you have the low flows that are penalized. This is extremely important to get an overview. Let me now get back to the question. How can we write this mathematical relationship? First, then, get an idea. Get an idea of the processes, what you need to reproduce. And then, let's make a consideration. We are talking about water that moves. We are talking about water. We want to describe movement of water. You will read there. Schematize the dynamics of water flow within the water cycle. And therefore we deal with the transfer of mass. We deal with transfer of masses of water, which take place at the expense of energy transformation. So you have the rain reaches the ground by converting potential energy into kinetic energy, and then the rain flows, the water flows along the hill slopes or in the underground by means of energy transformation. And so we are talking about fluid mechanics. What happens in fluid mechanics, mechanically fluid, is movement of water at the expense of energy transformation. And let's consider that when we talk about fluid mechanics, movement of water, we know one important thing, that conservation of mass and conservation of energy are always satisfied. So this is the first idea that we need to elaborate. I'm talking about fluid mechanics in rainfall model. Let me refer to conservation of mass and conservation of energy. And of course, conservation of momentum, quantità di moto. And also what we know is that Newton laws apply. And let's remember what are Newton laws. You well know them better than me, but let's try to refresh the concept. The Newton laws are three. And the first is, as you know, that every object in a state of uniform motion tends to remain in that state unless an external force is applied to it. Second law, the relationship between mass and acceleration is given by F, which is the external force applied to the element, the body that we consider, equal to the product of mass times acceleration. And then the third law is for every action, you have to expect an opposite action, which is equal but in the opposite, equal but opposite. So neutral laws are conservation laws. So the first thing to think about is conservation of mass and conservation of energy. And these are conservation equations that we are well used to deal with. So in principle, there is nothing complicated. The complication arises when you try to describe the geometry of the system that you want to describe and other things. But in principle, there is nothing very complicated. Let me do one thing, because this slide is not really easily readable. This is a picture of a catchment. Let me delete it just for 1 second. An important concept here. I said in principle, the concept is clear and quite easy, but there is one but. And the but is hydrological processes are typically very heterogeneous in space and are extremely variable in time. So this is a problem because this conservation equation, which I mentioned before, I said, okay, let's apply conservation of mass. This conservation equation, when you apply them, you well know that you have to refer to a control volume. So you have to refer to a volume in space where you want to operate the balance. And I already mentioned this concept when I said that water resources management is just a water balance. And I said, you need to define a region in the space where you compute this water balance. Can be a city, can be a watershed, can be whatever. And the problem is that if the volume is heterogeneous, so if I decide to use a control volume that is extended like a catchment, and I apply the conservation of water, mass of water, to the catchment, but the catchment is heterogeneous, meaning that the water is not uniformly distributed. There are parts of the catchment where you may have a lake and you have concentration of water. And there are parts which can be arid in the same catchment, maybe because it's very steep and there is no vegetation. So, if you try to describe with just one conservation equation in a heterogeneous environment, what you obtain is an indication that is valid only in average. So, if I want to apply the average water that is available in the catchment, then fine. I can apply the conservation equation to the whole catchment. But I have to well keep in mind that this is an average value. When we apply our equation to a control volume, we always get average values. If the volume is homogeneous, then that's fine. The average describes every single point into the volume. But if the volume is heterogeneous, then I don't describe the internal variability. But the problem is that in many applications in hydrology, I need to know how much water is available in a specific location. And therefore, this means that the control volume must be reduced. I cannot apply the conservation equation to the whole catchment, which would be easier. I need to apply the conservation equation at local scale, and this is what is written here. And therefore, this is a huge complication. Because if I want to write a conservation equation to 10 volumes instead of 10 1, 10 small volumes instead of a big one, I need to get the information for all these 10 points. If I want to describe the water availability in any single point in a catchment, for any single point I need to know the land use, the soil use, the soil type, the geology. So the information, first of all, I have a multiplication of equations. Because of course, I increase the amount of the control volumes, I increase the number of equations. And then I get a multiplication of information that I need. And this is a very important issue, which will bring us to distinguish between two main categories of rainfall runoff models. If the model is applied at the catchment scale, the control volume is a full catchment, the model is called lumped. Lumped, L-U-M-P-E-D. If the model, if the catchment is split in subunity, the model is called distributed or spatially distributed. The terminology would be spatially distributed, but then it's often abbreviated in distributed. So this is the first question that we have to ask ourselves. Would we like to apply the model at the catchment scale? Can we use a lumped model? Or do we need to reach a higher level of detail, and therefore do we need a distributed model? This is the first question. And by keeping in mind that the lumped model is much easier to apply. Of course, because